This session introduces us to the world of actuarial modeling. So, why we get into actuarial modeling? What do I mean by actuarial modeling? What are the various steps involved in this creation of actuarial models? What are the main advantages that are typically derived by creating these kind of models? What are the key drawbacks or disadvantages associated with respect to these models, and with a key differentiation between two major types of actuarial models? We deal with two major types of actuarial models, one being the world of deterministic models and other one being the stochastic models. How do we differentiate between these two kind of models? And then a little bit of introduction towards the state space and the time dimension, which we will discuss in more detail when we are dealing with the stochastic processes later on. And how do I assess whether the model is a good fitting model or not? Whatever the model that I have created, is it more resembling the real world or not? Right, the kind of mechanism, the kind of actuarial model that we have created, can it be used for the future predictions and future calculations? And what kind of time frames do we really get into the modeling process? Do we generally focus on short term or long term kind of stuff? And what are the various mechanisms that are involved in terms of validating and verifying the model? And how are the typical results of the model communicated to all the related participants and the parties? Those are some of the key things that we look at as a part of this particular topic on actuarial modeling. So whenever I'm starting out with the key steps that are involved in the modeling process, I'm starting out with the objectives. What are the key objectives that are intended as a part of the creation of the model? Is my intention of creating the model to predict the death rates, or to design the premium for a set or for a kind of policy, or for setting up some kind of reserves, or for some kind of investment decision? What is my key objective in terms of doing this actuarial model? And whenever I'm defining a model, obviously there are a set of inputs which come from various sets of assumptions and some kind of calculations that are happening on these inputs, which I typically call them as process or calculations, and this will result in terms of output. The output could be an investment plan, or it could be a death rate. So from as the assumptions keep changing, this model will automatically update, and that would result in the variations in the output. So the first thing that we are interested in the modeling process is what are the objectives that we are looking at. And from that objectives comes the plan, including the resources, including the mechanism, including the validation process. How do I compare it with the real world? All those things come as a part of the planning process. Then the data collection comes up, where associated relating to my objective, I would collect all the relevant data in the necessary formats. And I'm also looking at the various parameters that would be going as a part of the model, which means if I am fitting, let's say, a linear kind of a model, then y equal to mx plus c So what does M look like? What does C look like? These are the parameters of the model. So the various parameters I would be interested in, and probably I'm looking at understanding the real world system also thoroughly, so that I can really assess all the inputs that could go as a part of the model that is getting created. And probably I will interact with the experts, industry experts who have a good understanding of the real world system, so that a very good feedback comes to us once we have designed the theoretical aspects of the model. And from there I get into the software part, because once the design, so this is where the requirements or the data collection happens. This is where I design the model at a broader on a broader note. Then comes the development of the model part, wherein I will look at what kind of programming language to use, or probably what kind of simulation mechanism that needs to be used for the development of the model. So I would be more dependent on the software selection part of it. Software selection for the implementation or for the creation of the model. So once I am sure of it, I will write the program. I will do the debugging to test if there are some kind of program related errors or flow related errors. And that's where I get into the next step, which is the testing process, where I will look at the reasonableness or appropriateness of the program that I have written, giving some decent regular common input. Is the system generating the regular output as well? So then we are doing some kind of small sensitivity testing, right? Sensitivity analysis, wherein we are changing the inputs, one or two inputs slightly, and see what kind of impact that this carries on the output, and see what are the various kinds of outputs that are coming out of the model, what is the pattern of the outputs that is coming out for different levels of inputs that are being provided. And finally, once we are done, look out if there are any kind of compliance related issues in terms of how the calculations need to be done, any compliance issues with respect to data model creation. Look at the compliance related stuff, and once everything is fine, choose a proper communication mechanism to communicate the results to all the necessary parties. So any kind of a model that we are getting into will really involve all these processes, and once we have implemented all of them thoroughly, will create a well defined and well used usable kind of a model for all actuarial purposes, right? Now, why do we need to really get into this entire modeling process? What are the advantages that I can derive by getting into the actuarial modeling process? See, generally a lot of actuarial processes, especially when I deal with something in the life insurance space, I talk about policies ranging for almost 20 years, 30 years kind of mechanism. Or even when I'm looking at something like a pension fund, probably the duration of operation of this particular fund is 20 plus years. So I may, so if to understand the various learnings of the fund, and probably to look at the possible returns on the fund and all, I cannot wait for 20 full years and then incorporate the learnings and the advantages. But if I am creating a model, it helps me study long term behaviors very quickly. The long time frame products can be understood in a very quick time frame using a model, because I am trying to reflect the real world system through the typical model. So probably one advantage I could see is the systems which have the long time frame can be studied and understood quite comfortably with the creation of model. Then any system which has stochastic elements. When I say stochastic elements, the inputs that go into the model are not fixed. Rather, the inputs will vary following some distribution. The input elements, probably if I am talking about the sales growth as one of the input, or probably if I am looking at the GDP growth of the country, it may not be a fixed percentage. For the next year, it may not be a fixed percentage. Rather, it could be a variable, probably lying between, let's say, 5% to 8%, or probably following some kind of a probability distribution. Okay, it could be 5% with a probability of 0.3, it could be 6% with a probability of 0.4, something like this. So these kind of mechanisms where the input elements are not fixed, they could keep varying. We call them as stochastic elements, and any kind of a process which has heavy stochastic element and lot of correlation between the various inputs, we can study them quite comfortably using a defined model. And comparison of the various models can be done under various assumptions, and what kind of future impact each of these assumptions will get into the future. When will the company run out of cash? In what cases the expenses could be much more than the premiums that are getting collected? In what cases the cash flow shortages are going to occur? All these kind of things can quite comfortably be understood in advance by creation of various of these kind of models. And because we are controlling, right, we get more and more control on the operational elements, because we can very well create, we can very well fix the assumptions, we can very well control the environment, and we can try to see by changing the different kinds of inputs how well the output could be impacted because of this. So overall, I could see that there are so many positive elements that are associated with the model, but at the same time, creating creating a virtual real world scenario, creating an environment which almost reflects the real world, requires a lot of expertise. I require people who can visualize that kind of behavior. It requires a good amount of investment in generating and creating a kind of a model. There's a huge time that is involved in the creation of the model. So overall, there could be a heavy cost that could be going in terms of implementing this model. Though there could be a lot of benefit that can definitely come out of it, there is a huge cost involved. So which means from any company's perspective, a cost benefit analysis is very much necessary. And with all these things also, if the inputs are good only, because model is more like a framework, so only if the inputs are good, our outputs are good. So not just the creation of the model, we should have good inputs to give to the model also. We should be very much careful about how the inputs are to be given for this particular model. So here the model is trying to give, helping us more in terms of comparing the results, different inputs, different outputs, but it is nowhere giving me any kind of a hint in terms of how these results need to be optimized for better usage. None of that such kind of stuff is being given by any of these models, and there is a heavy reliance on the input data. So if the input data is not good, if the input data is challenged, so is my output. So whatever the effort that has gone, into the building of the model will become completely futile. And so it looks as if models can be run only with computer. So probably model, it looks as if the model is purely system dependent, and it even gives some kind of a false notion that I don't need to know the concept, right? There are a lot of people who can come out with this. I need not, no need to know the concept. My system will take care of it. So that gives some kind of false confidence among the people that we only need to interpret the final output that the model gives, and I don't need to know the process that has gone as a part of the model. So there could be a the learning can get very badly hampered. So it's as good as the model appears like a black box. I know how to input, I know what comes out of, and but I don't know what has gone in and how the output is getting generated. So in what cases the model is good to use, in what cases the model will have limitations, none of these things will be understood by the users because there's a lot of black box kind of a usage associated with the model. And visualizing the model with all kinds of future possibilities is very much close to impossible. Mean any change that comes in the future, probably the model upgradation is very much required. Means I need to understand the current aspects of the model so that the future can be taken care of at least to some extent. And in some cases it may so happen the model gives some kind of outputs, and interpreting all the outputs in a very business applicable manner may become more and more difficult. Because of all these reasons, we see though on one side a model looks more and more better in terms of usage, it goes with a lot of limitation factors also, and so probably a cost benefit analysis or enough care need to be taken care of while going forward in terms of writing the model or developing the model and implementing the same, right? And we also, in this context, we are also trying to look at the two kinds of models as I have just now hinted out. A stochastic model is one where the inputs are not fixed. Inputs, they vary according to some probability distribution. So the input that we are giving to the model is not one set but multiple sets of inputs. Whereas when we are talking about a deterministic model on the other side, it's only one set of inputs that are being given to the model, and we are testing out the output. Whereas when I'm going with a stochastic, the inputs are changing across, right, as per a different probability distribution. The inputs are changing, which means I will get series of outputs, and these outputs I will look out for a distribution of these outputs. I'm not looking at one single value for these outputs, I'm looking at the distribution of the outputs. So the input could follow one kind of a distribution, the outputs can follow another kind of a distribution, but at the end I am primarily looking at not just one input but a series of inputs and seeing how the series of outputs are getting generated. Whereas in a deterministic model, I am giving one set of inputs and I am observing one output. So that's the reason sometimes people say a deterministic model is a special case of the stochastic model. One out of the multiple inputs that are going as a part of the stochastic model, one kind of an input that is going in could be a deterministic model input. So that is what is the relationship that I can look at between the stochastic model and the deterministic model. Now, when should I choose what out of these? As we are seeing, this requires a huge effort because a distribution of the inputs need to be identified. distribution of the outputs. Powerful program needs to be written so that all kinds of inputs are executed every time and all sets of outputs are generated, stored, analyzed, evaluated. A lot of things are happening as a part of the stochastic process. So a lot of expertise, budget, lot of other things are going on as a part of stochastic modeling process. There's a huge time consumption because a program would be written which will execute all possible inputs to generate all possible outputs. But on the other side, if I need to execute a deterministic model, everything is on the lower side. I just need to consider one set of input. So write a program or write a model which would test for those set of inputs and that's it. So the more the complicated the real world problem is, if the real world problem is more and more easier, then probably a deterministic is good enough. But if the real world is problem is complicated, means there are multiple variables, input variables. There could be a lot of internal correlation between these various input variables. Then it is very much better to go with a stochastic model itself, because it becomes very much difficult taking one case and then using that case to build the model. So the more and more interrelationships existing between the variables, the more number of variables that are existing, the more complicated the distributions that are existing, it's better to go with a stochastic itself. But before going with it, just see if there are any existing models, what are the kind of models that are there, and what is the purpose. I mean, is it do we require so much of sophistication as a part of our model, or is it a very plain, simple conveying of the result? If more and more heavy levels of sophistication is required, yes, it is necessary that we go with a stochastic model itself. Otherwise, we can very well go with any kind of deterministic also. Also, on the other side, it's better that we check out for the regulation if there are any regulatory related things with respect to the model. Do we need to check out from a stochastic model standpoint before releasing it to the public, or we can rely on the deterministic as well? So those kind of things we need to check, right? And even if we use a stochastic, as we said, the deterministic is a special case of the stochastic. So sometimes what people do is they build a stochastic model and take probably the mean of all the various inputs, probably variable 1. Instead of a distribution, they take the mean of that distribution or the median of that distribution, provide one single value of variable 1, variable 2, variable 10, the correlations between each of the variables, and try to that becomes a deterministic input because there is one set of values that are taken for each of the variables. So with that one set of values, they try to test the model. Correct? With one set of values, they test the model, and that becomes a deterministic test. So model is built stochastically, but the testing is done deterministically. That's a better combination that can very well come out, as a part of the using of a particular model. Now, coming to the next aspect, how is the suitability of the model determined? How is this model suiting for a particular objective? Because every model that is getting created, it has an objective in mind. It could be for computing the premium, or it could be for setting the reserves, or it could be to perform some kind of valuation for an investment decision. There could be many kinds of objectives that are associated with the model. So we are primarily checking out whether the data that we have used to build the model, is it appropriate, is it accurate, is it fitting the purpose. That is one level of exercise that we are looking at. What are the kinds of errors that are possible with the various parameters that we are considering as a part of the model building? Are they more and more reflecting the real world? Are they very much deviating from the real world scenarios? So the understanding of the parameters, the values that are getting determined for the parameters, what are the kind of deviations from the real world scenarios, and what are the various variables that we are considering, and what are the kind of correlations that are existing between these various variables that are in the real world as well as in the model. To what extent there is some kind of coordination between what our model has generated and what the real world is, and what is the kind of relevance of all the outputs to the current real world, because I might have used the data sometime, I might have given the data sometime old. So we are looking at what is the kind of relevance to the current situation, what is the credibility, from what kind of sources did we get the input, what is the kind of credibility that is associated with the model input. So I can very well look at the credibility that is associated with the data inputs and how the outputs are reflecting the real world. And sometimes there could be a case of spurious accuracy. Means my model could give a very good accuracy. My model could very well say that there is a good amount of relationship that is existing between the inputs and the outputs, but in real world that relationship need not be there. For example, I have created a kind of a correlation model, let's say between my company's sales my company's sales and let's say the GDP of Uganda. Probably my company being in India may or may not have anything to do with Uganda. But when I'm trying to do a correlation between the two, probably it may come out as the correlation is very strong, because if the GDP of Uganda is growing, probably parallelly without any reason, even my company's sales are also growing. These two are independent, but they still are, because on the growth path it may so happen that the statistical relation, the model based relationship between these two might be so strong that it gives a kind of an impression that there is a very strong relationship that is existing between my company's revenues and the GDP of Uganda. That kind of accuracy is what we are calling as the spurious accuracy. So these kind of things we really need to check out before we are going ahead in terms of using our model for predicting and forecasting purposes. And that is where one more dimension that people look at is, should we really target a long term model? Should our model target more of a long term or a short term? Because in long term, we all know that no assumption can be fixed, right? Probably the volatility is very high, all the inputs can change drastically. Probably the pattern, the distribution associated with the inputs could change with the period of time. So the trust or the reliability that is executed, that is associated with the inputs associated with the model, will go very badly affected. So predicting all the long-term changes and then incorporating them into the model, they all become more and more difficult, which means if at all my model is becoming a long-term perspective, then we may have to suspect the goodness of fitment of the model. So and that too, if majority of the models they can very well build the relationships between the variables, correlations and all between the variables. In the short term, they look more and more relevant, But the moment we are looking at long term, the variables, the distribution, the correlation with the other variable, all these things can very well be questionable. So that means I cannot use any of these values which have been more and more appropriate from a short term dimension. That is where we really need to spend more time, understand the situation before we are going ahead implementing the model from a long term perspective. So majorly when we are doing a validation or the assessment of the model, we are looking at how good is the model reflecting the real world scenarios. So I can give some kind of inputs from the real world scenario, observe what is the output that is generated by the model, what are the various assumptions, whatever the different assumptions that I have used to build a particular model, what is the kind of mathematical relationship I have used to build this particular model, what are the various parameters I have estimated in building of this model, how well they reflect the real world, how close are they towards the real world is what is generally tested as a part of our model validation process. So even if we are building the model from a short term perspective or from a long term perspective, I am trying to really check out all this entire dimension to finally assess the goodness of fitment of the model, and that is where generally people can get into the usage of what is typically accepted in the industry as a Turing test, especially in case there is a real world system that is available. What generally is done is a set of experts are given the outputs for a set of inputs, the output which your model has generated, and the outputs which are executed by the real world system. And the experts are asked to compare these two. They don't know which is generated by the model, which is generated by the real world system. And if the expert cannot differentiate between these two, then probably our model is a good reflection of the real world. But if the expert is able to differentiate between the model's outputs and the real world output, then we need to take the input from the expert, find out what was the logic or what was the areas which made him spot the differences clearly. So use those inputs for enhancing the model. That is what typically happens as a part of Turing test process for validating the model. So that's one more way people typically look at evaluating the credibility of the model or the reliability of the model in terms of it modeling the real world situation. And there are other ways in terms of doing the validation. One, I can get into sensitivity what if kind of analysis by changing a few input parameters, seeing how well the outputs are responding to the input. So we can get into some kind of sensitivity, some kind of simulation kind of mechanism to change the input data. So primarily they are targeted towards what we call as what if analysis. Change the input, see how the output varies, looking at the robustness of the model. If the inputs are changed slightly, the output also should be changed slightly itself. How, by what extent the output is changing, the drastic change in the output with respect to the changes in the input is what is coming out through the sensitivity analysis. So what is generally done is there's a small change that is done to one or two input values, especially generally it is one, And what we are typically observing is what is the change in the output, and is that change more or less a real world kind of a behavior or not. And in some cases the same, instead of just giving one or two values as a part of the change, we are doing a big set of values. We are taking different sets of values following some kind of a distribution, using a computer giving different kinds of inputs to different parameter values and trying to see how each of the outputs are coming up. So especially we are using this kind of a process, different sets of inputs, checking different sets of outputs and seeing whether majority of these things are typically following the real world behavior itself or not. And finally, we are getting into, once we are assured that the once we are assured that the sensitivity and simulation, they are in line with the real world behavior. Next comes the final step, which talks more about in terms of how do I communicate the result. And basically here the intention is to identify all the recipients of the information, what is their typical level of understanding, at what knowledge levels I think I should be able to communicate. Should I talk too much technical with them, or do I need to talk more from an output perspective, or do I need to translate the output more in terms of business terms? So depending on the recipients of the information, the appropriate reports needs to be designed and communicated to the appropriate parties in an appropriate manner. So this is what typically goes as a part of any actuarial modeling process. This is a well-defined kind of a process which will be applicable for any kind of a business objective involving the creation of actuarial model and testing of it. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.